Morning, everyone. So today we're going to continue our next study. So we have finished until line resistance. Okay. So now we are going to the inductance. So this part of inductance, you need to be very careful. Maybe at some points it may confuse you. Okay. Dia ada beberapa part of inductance lah. Okay. Okay, first of all, we are going to find inductance for the basic one, which is a single conductor. A single conductor means that we have only one cable lah. Only one cable. Ni cable. Only single conductor or single cable. Okay. So a current carrying conductor produce a magnetic field around the conductor. Okay. When there's a cable, so the cable inside the cable the current is flowing from the plus terminal to the minus terminal. So when the current is traveling through the cable, it produces a magnetic field. Okay, a magnetic field, or we call that as magnetic flux, can be determined by using the right hand rule. So it means that when there's cable. So let's say the direction of the current is this direction. So you use the right hand rule. You use your right hand rule. So you are going to get this kind of direction of, we call that as magnetic flux. Okay, then the magnetic dalam direction ni. Okay, use the means the magnetics. The magnetic field is moving clockwise. Okay, clockwise if the current is in this direction. Okay, use the right hand rule. Okay. Okay, for non-magnetic material, the inductance L. Okay, here we have a new item here, which is the inductance L is the ratio of its total magnetic flux linkage to the current I given by this equation. This equation is fixed already. L equal lambda over I. I is current, lambda is the flux linkage in Weber turns. Okay? This is a very basic equation for this inductance. Okay, let's say we have I just draw the cable. So if we take the cross-sectional area of this cable, so it becomes like this. It becomes like this. So where this is the inside the cable, the area of the cable, while the outer part is not the cable, but you can see there's a dotted line here. So this dotted line, we call that as magnetic flux. Okay, so this dotted line means there's two parts here. The bold black one. So this one, I will say that this is the surface of cable. Okay, means this is the surface of the cable. So inside is the inner part of the cable, and the outside is the outer part of the cable. So both you can still see there's a dotted line here, which is they are fluxes. Okay, inside and outside. So ini adalah flux. Titik-titik ni semua titik-titik ni adalah flux, magnetic flux. Dia ada dalam dan luar. Dalam dan luar. Bukan luar saja, bukan dalam saja, tapi ada both. In both direction. Okay. So we imagine that the conductor with radius r. So this conductor have the r, ni r. So r ni jari dia, jari. Okay, jari dia or radius lah. This cable. Okay. Carrying a current I. So this cable are carrying current I. So macam mana kita nak dah penuh kat sini. Macam mana kita nak relate how can we relate between the I and the, we call that as the magnetic flux, okay, magnetic field intensity. So how can we, so this magnetic field intensity we call that as H, okay. So I equal to area, okay, because you integrate the value. So this dx, and from 0 to 25. Why 0 to 25? Because the circle one. So from 0 to 25. Okay. So you simplify it, so it become like this. Hx is the magnetic field intensity around a circle of radius x. Okay, x is constant and tangent to the circle. So this is the basic equation. For me, if you want to deeply understand this kind of things, you can refer to the notes uploaded in the column. Okay, kalau you open the column, open column at notes, teaching and learning materials, and then you go for chapter 3. Okay, inside the chapter 3 there is a docx file. Okay, you go for the chapter 3 line resistance. Okay, then that one, there's the word file. So dalam word file tu, dalam sekitar dalam page 14 kot, maybe around 14, then there's details about this 14, 15 after that. Okay. I just give you the reference. Yeah. So in other words, we just accept that there's a equation of this. Hx equal to Ix over 2 pi x. Okay. So this for the single conductor. So what is the relation between the inductance that we are talking about? So the inductance of the conductor can be defined as the sum of contribution from flux linkages, internal and external. So like I told you, so the total inductance for that specific conductor, so it's actually the sum between the, oh saya digulung, tahu ni, ini adalah outer part cable lah ni, ni cable size kan. So this is the external and this is the internal lah. So the total inductance of the conductor is the sum of both external and internal. Okay. External, there's a detailed calculation to this, will be influenced by the other phase conductor. Once we have the other conductor, so it influences at the external part. Internal, most of the cases are fixed. Okay, are fixed. There's no difference, but the external is totally influenced by the cable beside that cable. Okay? If we have another cable that beside, totally sitting beside this cable. But I just go through. So okay, here there's another expression. Because we are going to use this kind of values in the calculation after this. So this is the, basically this is the cable, the outer part of the cable. Okay, so there's a parameter we call the D1 and D2. So D2 is the distance from the middle until there's some points here, which is infinity. But what they're saying that the outer is D2, of course lah. The inductance is lower. The magnetic flux is weaker. That's logic. That's the logic. Okay. So just to say that the X is the cross radius of the magnetic flux. Annoying lah di belakang. Can you hear me? Is it okay?
Okay, that's okay.
Or you want me to shout?
No, 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 no need.
Okay. Alright. Nama pula dia mesin punya kat sini. Okay. Okay. When we have a single conductor, so that I told you before, we have internal and the external. Okay, internal and the external inductance. So means that when we have the single cable, okay, the single cable here, so there's the internal inductance, and the one is external. So both internal and external inductance have their own equation. Okay, have their own equation. Actually, so this is the internal inductance can be expressed as follows. So this is the final equation of the internal inductance for the single conductor. Okay, actually there's a derivation, a long derivation of this equation. But for me, for this case, I think if you want to go through the equation, you want to derive it by your own, you want to enjoy the derivation, I think you can refer the same notes. Okay, the same notes here, chapter 3, line resistance, start from page 15. Okay, di sini derive equation. Note chapter 3, line resistance. So this is the reference. Line resistance, page 15. 15 until 16. Okay, 15 until 16. For me, it's not important here to derive it because we don't have time. We don't have time to play that. So I think it's okay. Just take the final equation. But if you want to learn more, go on and go through this reference. Okay, this reference details. Okay, at last we get the internal inductance of the single conductor, which is half multiplied with 10 to minus 7 Henry per meter. Okay, Henry per meter. Where the mu 0 is the permeability of air. Okay, so internal inductance dependent is okay. Internal inductance is independent of the conductor radius. Means that for all conductor, most case internal inductance are the same because there's no difference between the radius of the conductor. Okay, the thickness of the cable is not influence the value of internal inductance. So ini dah equation dia. Equation dah ada bagi value dah pun. Okay. Okay, next is the external one. Okay, the external inductance. Okay, the external inductance between 2 points, which is the D2 and D1. So I told you the D2 is the most, I mean the farthest points from the cable, while the D1 is the nearest distance, okay, the nearest point, okay, from the cable also. Okay, so while the radius here is R, okay, with cable. So same external, there's a derivation also. So just go through, I think, from the page 16 until page 17, then you get the derivation, the full derivation. Okay, sama juga. Kita sama 16 to 17. Maybe you can enjoy the derivation if you want. Okay, just refer to this note. Then at the end, so here the difference is we have this value. Okay, this one is totally depends on the distance for this and this. Okay, so here comes the value here. But the rest are 2 multiplied with 10 to minus 7 ln d2 over d1. So only the d2 d1 is the variable that we have here. Okay. Any question? So equation ini. Any question? No? Tak ada ya? Ke dah terputus?
No, no, no.
Okay. Right. Okay. So next, okay, we're going to the next phase. Okay, we call it as a single phase lines. So a single phase lines consists of a single current, carrying line with a written line which is in opposite direction. This can be illustrated as we just imagine there's two cable. But different direction of the current. You see, and this one is the like screwdriver, is the plus one. So plus means that going inside the screen, okay, going through the screen. So that's why we have the if you draw the magnetic flux here, maybe around this direction. For this case, it's going out from the screen. So use your hand. So maybe they have this kind of direction of the magnetic flux. Okay. So this for the second case is we assume there's two phase conductor carrying current but in the different direction. One is here, one's in, one's out. So this is the second case, where each cable radius is R1. R1 kan motor the radius untuk yang cable number 1. R2 is the radius for the cable number 2. And the difference between the what we call it, between the middle of the cable of R1 to R2, so is D. It's separated with D, the distance of D. Okay, so the cable is separated at D distance. Okay, so this second case. So what should we do? So inductance of a single phase lines can be expressed as below, with an assumption that the radius of R1 equal to R2 equal to R. Okay, in this case, it assumes that the R1 and R2 equal to R. In other words, both cables are in the same size. Huh? So means kalau if they use the 2.5 millimeter square of cable, so another one also use the 2.5. Okay, if you use 6, then another one also 6. Okay, right. So like we have discussed before, that we have agreed before. So the total inductance is the sum of the internal inductance and the external inductance. Okay, internal and external. Okay, just use the equation just like that without thinking. Okay, so the internal inductance is half multiplied with 10 to minus 7. Okay, this one is internal, and another one is the external, where the D2 and D1 is applied here. Okay, it's applied here. Then okay, then you solve it. Okay, here there's some assumption here. Okay, there's some assumption here where okay, that is R1 equal to R2 equal to R. Okay, it's equal to R, and the D1 here. Okay, D1 here also is equal to R. So dalam case ni, in this case, saya ulang balik. So dia ada R kan, R dan juga D1 kan. So dalam case ni pun dia assume D1 tu sama dengan R. So maksudnya D1 tu adalah R sini, D pun sini, D1 pun sini. That's why dekat sini assumption dia, so B1 also equal to R1. So R1 equal to R2 equal to R. So that's why dia jadi R. Semua mata kat sini. Okay. So they solve the equation here, solve blah blah blah. Then simplify become ln to minus E 1/4, 1/4. Then solve E like this, blah blah blah, and finally they get the 2 multiplied with 10 to minus 7 ln D. D is the distance between the cables. Okay, this one. So this is the D. D is here. Distance between these two cables. So they get RE minus 0.25. Okay, they get RE minus 0.25. Okay, then okay, there's another new thing here. Tengok ni, ni ada RE minus 0.25. This is equal to R prime. Kat sini sebenarnya ada lagi definition. Kalau you tengok teks dalam nota yang sama tu, dia ada panggil R prime, which is this is the, we call that as GMR. So this is the GMR. Okay, GMR. So GMR ni apa dia? GMR ni is geometric mean radius. But in this equation we don't write lah GMR here. We can take it out GMR, or sometimes we write as R prime. Kita samakan dia dengan R prime. It's okay if you want to just leave it like RE minus 0.25, but there's a simplified version which is we call it as R prime, where the R prime is GMR. It's the same thing. Okay. So ini adalah the unit is Henry per meter. Henry per meter. Okay. For this inductance, the unit is Henry per meter. Henry per meter. If you check the same notes also, dia ada simplified lagi. Mana saya tulis belah tulis ni. N satu unit dia Henry per meter macam ni. Yang ini sebenarnya dia boleh lagi simplified untuk express dalam milli Henry per kilometer. So dia adalah L sama dengan 0.2 ln D over R prime in this unit. Boleh faham tak? Keserabut.
Doktor.
Ya. Yeah.
Dapat 1/4 doktor yang dekat formula line yang second tu.
Okay.
Dalam bracket ada 1/4 tambah ln D over R. OR tu I faham, tapi yang 1/4 tu macam mana doktor?
Oh, datang dari mana ni? Yang ni?
Yeah.
Macam mana dapat yang benda ni? Law ni?
Macam mana dapat 1/4 tu doktor?
1/4 you keluarkan lah. You keluarkan 2 multiply with 10 to minus 7, so dia jadi 1/4 lah. Faham tak? Ni? Ni kan? You keluarkan ni, you keluarkan 2 multiply with 10 to minus 7 kan? So of course lah dia ni 1/4. But dia kan originally 1/2.
Oh, okay doktor.
You keluarkan ni je. Kita nak samakan depan ni. Nak keluarkan ni je. Betul habis.
Doktor.
Ya.
Yang ni just dia punya derivation kan. So maksudnya yang final nanti kita akan pakai yang bawah ni lah, 2 kali.
Yang belakang sekali, yang bawah sekali tu.
Okay.
Kan macam tak perlu lah tunjuk ni, tapi nak tunjuk lah. Kalau tak tunjuk nanti
Ah.
apa pula. Gitu. Tak tahu lah dapat dari mana. Macam tu lah.
Okay.
Macam tu lah. Yang ni di dalam kilometer ni. Ni per kilometer ni. Per kilometer. Boleh? Okay. Jadi. Okay. Ini case yang lain. So the series, okay, there's a new term here, self and the mutual inductance. So the series inductance per phase can be expressed in terms of self-inductance of each conductor and their mutual inductance. So the mutual inductance, if you look at this table figure below, consider the 1 meter length single phase circuit in figure below. So there's 2 cables here. This one is cable 1. This one is cable 2. So this cable has their own inductance in total, which is the L11, and this one also has their own self-inductance, the L22. But there's another, we call that as L12, which is this is the mutual inductance. Okay, this actually from the external tadi lah. The external tadi dia ada lagi yang influence when there's the cable over there. There's a plus of the inductance also that comes from another cable that influenced by the another cable lah. So when you have a lot of cable circling around one cable, so the total mutual inductance also will increase for that specific cable. So each cable tu nanti kalau let's say ada satu cable, lepas tu sini ada banyak kan. So lagi banyak lah dia punya mutual inductance tu. Okay. So itu nanti akan cover banyak di depan. Ini basic dia. Let's say we have 2 cables. So this cable they have the mutual inductance which is the L12. Yeah. Here is L12. Okay. Boleh kan? Okay. Ini okay. So what should you do? This is also the derivation, but to make it understand, you need to know this one. This one only inductance for cable 1. Okay, this one cable 2. Okay, cable 2 and cable 1. Like we agreed before, this is the apa ni? Internal line, and this is the external. Okay, so this is internal and external for the cable L1 and for the L2. The different only the radius, and the radius is R2. Okay. Okay, this D is the different distance between these 2 cable. Not written here, but this one. Okay. Then lambda 1 is the flux linkage. Okay, flux linkage. Kan flux linkage tadi kita ada tadi kan. L equal to lambda over basic equation I. Okay. And it's a inductance, and this is the flux linkage in Weber terms. Okay. So the relation between this one lambda 1 is the L11 minus L12, and lambda 2 is the minus L21 plus L22, which is the L22 minus L21 like that. Okay. So I1 and I2. So this is the berkata equation. Okay. So L1 equal to L1 multiply with I1, which is the L1 actually is coming from here lah. Ni L1 ni adalah L11 minus L12 sama equation atas ya. Okay, ni. So we just substitute the value of the L1 here. Okay, ni value ni kita substitute dalam ni. Okay.
Masa?
Ya.
Tu 2x ke 2 darab 10?
Darab. Biasalah disilap.
Okay, okay, okay.
Oh, mata tajam. Darab. Okay. Lepas tu, ini yang semua. Then, here they separate it. And they separate it dengan minus lah. Okay. So, separate ni, okay. So, L11 ni belah sini. The first term ni L11. And this one is the dia tulis sini minus L12 lah. So which means that ni akan jadi negatif lah. So that's why L12 ni sonang lah. So dia adalah 2 multiplied by 10 to minus 7 1 over D. Kita terbalik je lah. Ln kan. So dia akan dapat. Tara. So at the end, so once we get the L12 untuk dapat L22 tu kecang lah. Kecang lah. So at the end, L11 ni sama dengan L22, beza ni pada R ni. Okay. And then L12 is equal to L21, which is this is the mutual tadi lah. This is a mutual inductance. So inductance is now 1 over D. Okay, 1 over D. So ini bolehlah kalau like I told you lah, dia macam ni lah. Ln 1 R prime 1. Kalau nak pakai R prime lah, tak ada apa pun, dia sama. Ni R prime, R2 prime. Okay. Ni equation dia. Just go through the equation. Okay. Lepas tu, so flux linkage of the conductor. Okay, flux linkage of the conductor. Sekarang tadi kan, flux tadi L sama dengan L over I. So flux adalah inductance multiplied by I. Okay. So kalau kita nak express dalam Li tu, so macam saya cakap tadi lah, kalau ada lebih banyak kabel yang ada sebelah-sebelah dia, so at the end dia akan jadi macam ni lah. Ni untuk kesnya kalau ada apa saya panggil tulis ni lah, conductor I. Kalau dia adalah sum of the other kalau ada satu kabel, ini kabel kita, ini kabel I kita, lepas tu dia ada kabel keliling tu kan. So kabel keliling tu adalah hasil tambah dia lah. Original ni datang daripada dia sendiri, yang the rest adalah yang coming from the cable or the phase conductors beside the main cable. Any question? Faham apa macam ni? Boleh tak ni macam kita macam lebih more to go through the equation lah. Apa yang kita telah lalui untuk hari ini. Ya, saya return balik. Balik sekejap sebelum korang confused. Okay. Mula-mula sekali, Allah akan buku. So ini adalah single conductor. So single conductor kita ada boleh sekejap. Sekejap. Okay, apa kita belajar ini? So, no single line conductor. Okay, daripada single line conductor ni, then so we know that the total inductance is the sum between the R internal plus R external, L external. Okay, so the L internal decide already, boleh tulis terus je. Okay, minus 7. Okay, ni dalam unit Henry over meter, then plus with the 10 to sini. Dua. 10 to minus 7. Okay. Ln D2 minus D1 Sini. Oops. D2 minus D1. D2 over D1. Okay, D2 over D1. So it's the same unit. So, okay. Henry over meter. Okay. Then okay. The next is the single phase. Okay, single phase line where we have the two cable. The two cable. The two cable. So between these two, they have D, okay, and they have their own R1 and R2. But in this case, they assume, okay, so they assume, here R1 equal to R2 equal to R equal to D1, okay. Ini punya assumption dalam case ni. So in the end, yang last kali tu kita dapat L equal to 2 minus 10 to minus 7 ln 1 over R prime, okay, R prime plus 2 10 minus 7 ln D over 1. Okay. But in the end dia dapat ln 0.2 ln D over dx ni adalah R prime. Okay. Ini dalam unit milli Henry over kilometer.
Yang tu untuk kabel lah kan?
Betul? Ini untuk in case kabel itu dua kabel, lepas tu dia punya radius dia sama, R1 dan R2. Dia sama adalah arah between the distance dia dari D ni. Then ada satu lagi, okay, yang bila kita boleh breakdown kan dia, so breakdown kan untuk kita nak kira self and mutual inductance tu. Okay. So yang kat situ ada L sama dengan L1, so L1 punya internal plus L1 punya external, and the one is L2, so L2 punya internal plus L2 punya external. Ini kita go through dia punya yang tadi kan, ni kita kira semua ni, dan finally kita dapatlah dah sekali equation dia bunyi, okay. L11, L1, L22 dan 2 mutual, dapat mutual inductance dia. Ini memang totally untuk case yang dua kabel je lah, dua kabel yang mungkin ni kan. Nampak ni dua kabel macam ni kan, okay, dua kabel tu. Dan kata lain daripada sini ni, daripada 2 ni terus 3 ni dah. Okay. So ini adalah yang kita kira tu. Ini untuk two cables. Okay, two cables. Okay. Kita ada dalam 12 minit. Cik kita buat ni. Jom buat ni. Okay. Exercise and 132 kV, 50 Hz, single phase, 2 wire kV, 2 wire transmission line. So maksudnya kita dah dapat agak lah. Dia berupa begini lah. And dia berupa begini. So then of aluminum conductors with diameter of the 50 mm. So ni dia tulis sini adalah diameter lah. Okay, dia dalam diameter. So diameter sini adalah 50 mm. But in the calculation we need the R kan? R. Tak. So R sama dengan berapa? R sama dengan?
Satu 1.8.
Oh my god. Come on guys.
25.
25 ya. Marahlah Fana. Jangan marah Fana. Okay. R adalah 25 mm. Itu dia. Lepas tu, the two conductors are spaced. So space dia kat sini lah. So dia punya D kot adalah 1.8 meter. Okay, 1.8 meter. So means that ini pun awak kena tukar bermeter lah. Kan? So ni kalau jadi meter, akan jadi 0.025 lah. 0.25. 0.25 meter. Okay. Then what's next? Transmission line is 25 km long. 25 kilometers long. So kabel tu sepanjang 25 km long. And the temperature of the conductors is 20 degrees C. Okay. And we have the punya rated base dia kan. The 132 kV and the 50 Hz. Okay. So dalam ni kita nak apa nak kena buat? So kita nak cari series resistance kan per kilometer kan of this transmission line. So at the end apa yang kita nak cari sebenarnya? Kita nak cari apa sebenarnya ni? L sama dengan? Sudah. Hello? Kita nak cari apa ni? Cari inductance kan? Memang cari inductance lah. So kita nak cari apa sebenarnya? Dia nak dalam kilometer. Apa nak cari sebenarnya? Dia dah ada R. Kan? So kalau tak saya cek ni lah kan? 0.2 ln D over apa?
Cari yang kabel tadi tu
Itu lah. Cek yang tu je.
R.
R prime. Okay. Dalam milihenry per kilometer. So ni R prime ni sama apa? Sama dengan R E negatif 1/4. Macam kita?
Sir, kalau guna 0.25 boleh tak sir?
0.2 ni boleh, tak ada masalah, tak berdosa pun, boleh. Masalah sama je. So dekat sini kita mula-mula kena kira GMR lah kan. GMR ni R prime je lah. Kita kira GMR dulu. Berapa dapat? 0.025 E negatif 0.25. Berapa? Hello. Moshi. Kenapa senyap semua ni? Tidur ke?
Sir, R tu nak dalam meter ke apa
R meter lah. Sebab dia
Dalam meter.
ni okey lah kalau bawah tak nak meter, atas ni pun jangan meter lah. Kan cek pasal. Baik kita buat meter lah.
Oh, okey.
Tapi equation ini dia terus keluar final answer tu dah jadi millihenry over kilometer dah. Cek kira. Ni bawah 0.025 ni. JMR, berapa JMR?
0.0195.
0.0
195.
95
Ya.
meter. Betul juga kan? Betul tak? Dapat tak?
Dapat sir, dapat.
Okey. Jangan marah. Tergajang kan? Okey. So satu ni dapat dah lah kan? Berapa L dia? 0.2 ln ln ni log E takutlah orang tak tahu ln ni apa benda. Dalam kalkulator dia. Okay, 0.0195 millihenry per kilometer. Berapa?
Kosong 0.905 sir.
0.905 millihenry per kilometer. Betul? Betul kan ni? Dia kira ni?
Betul sir.
Betul lah? Okey, betul. So kita anggap betul lah. Okey, betul Okey, nombor 2 je nak buat nombor 2. Next, nombor 2.
Jarak dengan 25 kilo meter.
Yeah, macam tu je. Berapa? Cepat. Boleh 25 lah. Berapa? Nizaruddin berapa? Jarak dengan 25 je.
Dua 2.62 kot.
Apa benda? 22 point?
62
Betul ni. Betul lah kot
kilo.
Betul sir.
Betul
22.62 kilo.
Bukan kilo. 22.62 millihenry lah.
Betul sir.
Untuk 25 kilometer. So, per kilometer dia adalah is equal to 0.905 millihenry, and for the 25 kilometer you simply multiply it with 25, you get 22.62 millihenry.